Come on in, everybody. Yep, some more people coming. Anybody have any questions before we get started? No questions. Well, since it is technically time for class to start, I guess I'll just say make the announcement first. So what I decided to do is I'm going to let you guys take your midterm again. It'll be a different midterm, of course, but I'm going to make a new midterm practice, and I'll make a new midterm respondus practice. And this is completely optional. Nobody has to do it, but I'm going to be super nice, and I'm going to make it a online, but it has to be proctored via Respondus monitor and also Respondus lockdown browser. If you're willing to do that, or if you don't have a webcam, you'll have to go to a testing center to do it. That's fine too. But one of those two options are a necessity. So you got to either have the video done, being recorded, or you've got to, and you watched, of course, or you've got to go to the testing center if you can't do that because of your webcam or whatever. So I'm going to give you another chance, and I'll only take, here's where I'm being nice, I'm only going to take the higher of the two. So if you do the worst the second time, I'm going to let you keep your score, and I'm still going to keep the deal where if at the end of the semester you make a higher final than you did at midterm, I'll replace the midterm grade with that. But I think it would be worthwhile for you guys to do that. I'm doing it with all of my classes this time, just to let you guys know. So this will be something you take on your own at your own time. I will probably have the practice test made up tomorrow. If not, it'll definitely be available by Monday. And I'll probably put the actual second midterm attempt. I'll probably put it up by Friday of this week, and you'll have till probably Thursday of next week. So hopefully that'll help you guys make you feel a little better about the grades. You got to know, as always, the midterm grades were not that high, and they normally aren't, specifically because of the nature of you taking nothing but online tests, and all of a sudden you finally got to take a face-to-face test where you don't have all those features like Googling stuff, looking at your map, looking at your notes, looking at your textbook, all that good stuff. So does that sound good to everyone? All right, so I'm going to set up my good notes system. I got to make a new one, a new notebook. P each 241 and 01 B and underscore today's 11/2, right? 110222. Okay, so I now have my document made for me to record stuff and write stuff to you guys. So what I'm going to work on is we've done most of the kinematic stuff, so I highly recommend you go back and look at examples in the textbook. Now, I worked a pretty good robust set of problems last time for kinematics, and I think they're super easy. I hope you find that's the case. If you look though, you'll see plenty of examples in sections 10:1 through let's say 10:3. So you should probably make sure you can do all those examples all on your own. But one thing I want to show you is kind of neat. So one, we definitely use torque as a vector, and torque is R cross F. I hinted at that, or at least gave it to you last time. I can't remember. Either way, it's R cross F, where R is a vector that points from what you call the pivot point, or the central axis of rotation. If you draw a vector from that point right there to wherever the force is applied, and then you put that force where those two vectors are tail to tail, you take the cross product of that, and you will actually get the torque. Another way of doing it is multiplying the component of R that's perpendicular to the force, you can do that and find the torque, at least its magnitude. Or you can find the component of F perpendicular to R and multiply that by R, and you'll find the magnitude. Or you can just use RF sine theta, where theta is the angle between them. And you can R times F times the sine of theta, and that'll give you the magnitude of torque. But in all cases, we treat the vector torque as if it's a vector. It's kind of weird. Like if you have, let's say you have, this is the radius vector. So you imagine, for instance, this would be at the center of a wheel. Here's a pencil sharpener that looks like a wheel, right? So the pivot point is right here at the center. Okay. So if you imagine a vector running from the pivot point all the way out to the point of application of force, then that would be that guy right there. So let me now show you what the force vector would look like. So this is the R vector pointing to the force. That means if this ends the arrow for the force, then what you really want to do is find the component of this force, which could be at any of these angles right here. You want to find the component of force that's actually perpendicular to the lever arm. Okay, so all of this is assuming the vector is applied right here at the end of the R vector. Now that vector can be like all this and all that. And obviously each of those cases, you either got to find the component of R that's parallel to F, which would be like this guy, or you got to find the component of F, which is perpendicular to R, which is, this little part of it. Okay. Now, when you do a cross product like that, it's R cross F. So what I do is, this is one way you can use your right hand rule. This index finger would be the R. So it's pointing that way. And then my F would be pointing that way, say. And that's what I use the middle finger for. And notice they're like that. They're 90-degree angle. And then my torque vector, of course, would stick out of the page, or out of the top of this like that. So they're actually all three perpendicular. That's the way we call it. And that works fine for torque. What I will tell you is that we often try to make up some angular velocity or angular speed as if it were a vector. And the way you do that is you assume something's rotating and around in a circle. Now, if it's rotating this way, then I take my right hand and curl my fingers around that way, and that thumb points straight out parallel to the axis. That's the way it's supposed to be done. Now, if it's rotating the other way, then I got to put my hand this way and it'd be coming towards me. So for instance, if you're riding a motorcycle forward, that means the wheel is turning this way. So I would have to put my hand like this to account for which way the front wheel is going. And in fact, the angular velocity is actually pointing to my left. Okay. Same thing with the back tire. It's going like this. So again, pointing to my left is the angular velocity. Now that is in some sense a vector, but to be honest with you, sorry about that. It's not really a vector. It's what we call a pseudo vector. So what you can do to see that is you can imagine, for instance, looking at the reflection. So assume this is a mirror image, right? Now, if this thing is rotating this way, meaning the top is coming towards you and the bottom's going away from you, then that vector is supposed to stick this way. But if you now look at, and I didn't mean to turn the thing on. If you now look at the reflection, what you'll see, let's try to turn it down a little bit so you can see. You have to sort of imagine this now. Now remember, it was turning this way, which would mean the vector's this way. So if it's turning that way, the vector's this way. Well, if you look in the mirror image of it, which obviously this thing isn't acting like a mirror because it's black, but if I had a mirror, which I thought I'd find something shiny, but I did not find anything shiny. But anyways, if I had a mirror, what you'd see is back behind the mirror, this thing that's rolling this way is actually behind the mirror. It appears to be rolling the top away from us, just like the top away from us is going here. So the top back here is going this way. And if I do that with my right hands, that gives me a W or omega vector pointing that way. So the reflection of itself and itself are contradictory. When that happens, that means you have a pseudo vector as opposed to a vector. Okay. So technically, angular velocity and angular acceleration are something we can represent as vectors, but you don't want to take that too seriously. Like, it wouldn't be helpful for you to start adding the vector components and stuff like that. Sometimes it actually fall out. What we normally do is we just say, okay, it's going to be some quantity that causes rotation in the case of torque, and we're going to choose to make either clockwise or counterclockwise positive, and then the other one's got to be negative. But to show you something else about these angular vectors, like a rotation vector, for instance, that to show you that it's not a vector, you can also see that it's not commutative, meaning a plus b in vector and algebra world is supposed to be the same as b plus a. Well, if you think, let's imagine for a second that the x-axis is pointing into the page of the screen, but maybe out of it for you is fine. Okay, so my x-axis is pointing this way for me, and my z-axis is pointing this way. So if I do a 90-degree rotation about the x-axis first, that takes my, I'm going to stop a second. Now I'm going to start it. Now, if I take my tablet here and I do a 90-degree rotation about the x-axis, which comes out of my chest and goes towards the screen, then it's going to look like this. Now, if I rotate it about the z-axis 90 degrees, it's going to look like that. So if I want to undo that, of course, it looks like that and this. So what happens instead if I do the z-axis first and then the y-axis, or excuse me, and then the x-axis? So if I did the z-axis first, the z-axis, remember, we rotated it because I went this way and then I went this way, right? So if I rotate it first about the z-axis, that means it's going to go 90 degrees this way. And now I rotated about the x-axis, and now it's going this way. See how it didn't turn out the same way? So again, if I rotated about the x-axis first, like that, and then I rotated about the z-axis like this, boom, there it is. But if I do the z-axis first, which would be 90 degrees this way, and then the x-axis, I get entirely different things. So it's also not commutative. That's the big deal here. Okay, so that's the fundamental idea behind these using vectors for omega and alpha, and we don't generally do that. Okay, we can use it to make our symbols pretty and stuff like that, but they can actually cause problems. So you got to be very, very careful. Generally, what we do is when we're going to solve a problem, we'll write up in the top left-hand corner, we'll draw a vertical axis, a horizontal axis, and a circle, and you put a plus inside of that little circle. And what that means is if your circle arrow is pointing this way, you're considering that a positive torque. If your y-axis is straight up, that means that's positive as well. And the other axis that you drew is that way, that means that direction is positive as well. So that's how we indicate that. So to do that, I've got to introduce you to a few things. So I've already covered, for instance, the rotational motion analog equations. Of course, I did that on a video. I didn't get any text from anybody asking questions, so I assume y'all had a pretty good understanding of what was going on there. And the test questions are already, I mean, the homework questions are already up, so hopefully y'all have had a chance to look at those. Now we're going from the kinematics portion of this course to the dynamics portion of rotational motion. Now, the whole dynamics portion of the stuff that we learned in linear motion is still relevant. So F equals ma is still something that we have. I hate looking at my hat on. Didn't I have long hair just yesterday or something? I don't remember being this bald. Anyway, so when I'm thinking about dynamics, I got to think about, okay, what makes things actually accelerate? Well, we had F equals ma, which gave us three equations. The summation of forces in the x direction equals mass times acceleration in the x direction. The summation of forces in the y direction equals mass times acceleration in the y direction. Summation of forces in the z direction is equal to the mass times acceleration in the z direction. That's three equations right there just from Newton's three laws of motion. Now we've got a torque equation about a particular axis, and you can in fact do two more axes, or at least one more, one additional axis. So that would be up to two torque equations as well. So what we're going to do is deal with that. Let me start by sharing my screen. Anybody have any questions before we move on? Anything about last time that bothered you? You didn't understand anything you need to get off your chest or anything? All right. So what I'm going to do is share screen. Looks like everybody's good to go. I'm watching the chat too, in case y'all try to ask me a question via that. But also feel free to remind me if, you know, sometimes I might not see it until it's been up there a while. All right. Oops, did the wrong thing, stupid me. Okay. So this is our documentation. And what I was just telling you about was the Newton's second law of motion, which is F equals ma. Okay, so F equals ma, we normally write as the summation of the forces is equal to mass times acceleration. We write that in the vector form like this. And I learned the other day that this line can be, oh, there it is. That's how. Okay, I didn't really want it that thick. Now, what it turns out is there's a set of equations that can be represented by this, and it gets the vectorness out of it. It's the summation forces in the x direction equals mass times acceleration in the x direction. Summation forces in y direction equals mass times acceleration in the y direction. And the summation of the forces in the z direction equals mass times acceleration in the z direction. Okay. Now, if you're using a Cartesian coordinate system, that's it. But you could, of course, use other coordinate systems, in which case you wouldn't have a x, y, and z necessarily. You might have z, for instance, if you were using cylindrical coordinates, but you wouldn't have x and y. That being said, if you have to do any calculus on vectors, you still want to go back and root them into or transfer them into x hat or I hat and j hat and k hat notation, just because the calculus works out. Now, what's the equivalent of this in rotation? Well, in 3-dimension, you could have an axis, or excuse me, a rotation about the x-axis, a rotation about the y-axis, a rotation about the z-axis. It's very rare that you have more than 2 axes being used, but in principle, you could have 3. But the general vector form of this is the summation of the torques is equal to I times alpha. And this is that pseudo vector. That alpha is a pseudo vector that I was referring to. The torque, by the way, is defined as a vector to be R cross F. So let me draw a picture to help you understand that. Let's imagine we have a little hex bolt, hex nut, I should say, that we're applying a torque to. Okay. We're going to try to take that nut and loosen it by using a wrench. Okay. Now, you can say the center of that nut is the pivot point. And actually, it turns out you can use any point you want to be the pivot point, just like you can move a couple in statics anywhere you want, just by doing some minor stuff. Same thing happens with this. But if your force is applied, say, to this spot right here, you know it's going to be actually supplied to the handle itself, but we're going to pretend like the handle is infinitely thin or something. Then the R vector that we're talking about up there is this one. It points from the axis of rotation to the point of application of the force. Now, the force, on the other hand, might actually be something like this. In other words, maybe it's in a tight spot and I had to bend my arm all crazy just to get it in there. So I end up pushing this way. And you can see that's a bit of a problem because, in fact, you've got this component here and this component here. This component is just parallel to the rotation axis. So this one causes no torque. So this big chunk of force that we put in there is being wasted of it. This part, on the other hand, this is F perpendicular. And you could call that, for instance, if you said, let's say this angle is theta. Then let's say this angle is also theta. Whatever this angle is, for instance, between the X and that can be used. The main reason being, if I draw it in a different scale where you can actually see them, I'm going to take and move this red vector I'm going to slide it along this thing until it becomes head to tail or tail to tail, because that's the easiest way to make use of the formula that says the magnitude of the torque is actually R times F times the sine of the angle between them. You could also call that R perpendicular times F, or you can call that F perpendicular times R. That's three different ways you can calculate it. So if I draw these vectors separately, let's draw this vector. I'm trying to make a faithful representation of the R vector. So that's like your lever arm. Actually. Okay. And now I'm going to take this force, the red force, and try to put it tail to tail with this one. And it looks like it sort of goes like this across. It goes a width of about 1.5 over 4 cubes. So I'm going to say it sort of looks like it might be this. Now that these vectors are tail to tail, then you know that's exactly the theta they're talking about. Now, if you imagine a couple different ways, I can imagine a right triangle being made with one of its legs, the R vector, and the other leg being perpendicular to the R vector. Then this component right here is F perp. And you can see that's basically F times the sine of theta. This one, on the other hand, is F parallel, and that would be F cosine theta. Now, alternatively, we could actually find the component of R perpendicular to F. So if I drew like perpendicular to F. So if I drew like a little right angle there, then I could say, let's use red this time. And I'm going to say this vector is perpendicular to the force. Ooh, I actually didn't draw it that well. Whoa, not that. Nope, not that. Nope. 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 Okay. I didn't draw it very well, but it's supposed to be perpendicular, so I'm going to try to draw it a little better now. Still bad. Still horribly bad. Okay. So we could draw components like this that are parallel and perpendicular to the lever arm vector. That's right, actually. And this guy right here and this guy right here add up to give you R. This is R perpendicular to the lever arm. And since this red one right here and this red one right here is supposed to be parallel, then this obviously is the same thing as theta. So this is R times the sine of theta. I left off the R, so I'll say times R. So that's what R perp is. And of course, R parallel is R cosine theta. So you can see no matter which way you do, you can take either R perp times F, or you can take F perp times R, or you can take R times F times the sine of theta. But you really got to make sure you are doing the correct angle, and the correct angle is the smallest angle that separates them when the R vector and the F vector are tail to tail. Okay, so that's the problem. You've got to be able to do that. If you don't do that, it's going to screw everything up. Now that we have that, we can actually figure out what is I and all that stuff. I gave you a little talk about it last time, but I didn't really cover it as much detail as you need. So I'm going to tell you that I, if you're talking about, let's say, a bunch of like rocks or asteroids or something like that out in space, the asteroids might be, kilometers wide, like bigger than cities and stuff like that. And in fact, they might be orbiting some common center of mass of the gas cloud of gas, dust, and rock. And you could actually figure out what the moment of inertia of that whole gas cloud is. Now, the problem with that is it's not very physical, because if you're actually wanting to use that moment of inertia to figure out how hard it's going to rotate it, it's not a solid body, so it's not going to work out that well, because if you just grab one of the asteroids, you're going to move that asteroid and not do much to the rest of the system. So what you can imagine instead is, let's say we filled that space up with, let's say that spray foam insulation stuff. Then it'll embed the heavy rocks and asteroids. They'll be embedded in a location in space. And then all we have to do to find the moment of inertia is take the mass of each one and multiply it by the distance of that center of mass of that asteroid from that center of mass to the rotation axis you wish to rotate it about, and then square it. And then you got to do it for M2, R2, and square it plus ... So if you have a discrete collection of masses, they might be on a sheet of plywood, they might be embedded in a sheet of plexiglass, they might be in a ginormous solid shape that's made out of gel, and the gel's so white, so light, and so low density compared to the actual big things in it, you don't even have to take them into account. But if you have an actual continuous body, which is sort of what we have with matter, we sort of picture, a 2x4 is made as wood all the way through, and in some sense that's right. But if you actually look at the end of a 2x4, you see these little air holes and all sorts of stuff like that. If you took a big enough area, though, it'd be pretty much uniform density all over. But still, when you have that sort of material, and sort of the best way to think is maybe a big solid iron rod. If you have a big solid iron rod, then you can sort of pretend that's made of a bunch of infinitesimally small rectangles or rectangular solids, when in fact, it's actually made of individual atoms, but the individual atoms are so small, you really don't have to deal with it. But if that's the case, your moment of inertia is going to be not mr squared plus m2r2 squared plus m3r3 squared, but the integral of r squared dm. And the rule that we'll use is that dm is equal either to rho times dv, where v is a volume. So that density would have units of kilograms per cubic meter. It could have grams per cubic centimeter. It could have, pounds per cubic meter or whatever. Or it could be a surface density times dA. And in that case, the sigma would have units of like kilograms per square meter. So if it's like a two-dimensional object, like a sheet of cardboard or a sheet of sheet metal, the sheet metal thickness is very, very small compared to the physical dimensions of the sheet metal. You might think of, for instance, a caution sign, one of those big aluminum caution signs that are painted yellow. If you're talking about that thing rotating, you can treat all the material as if it's just really two dimensions, because that thickness, that itty bitty thickness, isn't going to be that big a deal. So that's when you'd want to say, okay, I'm going to just calculate the center of mass of that what we call a homogeneous two-dimensional lamina. And homogeneous just means it has a constant density. If you cut out any 1 centimeter by 1 centimeter by 1 millimeter, because it's about a millimeter thick, area, and weigh it, and then do that with another one at random, take it from it and weigh it, they're both going to weigh exactly the same. That's what we mean by homogeneous, meaning the density is a constant. Or if you have a sort of one-dimensional object, then it could be lambda times dl. Those are the things that you use to perform a calculation of this moment of inertia stuff. So I'm going to start off by calculating a couple of these moments of inertia just for ease. We have the torque equation. We know how to get that now. I should tell you also that in addition to the summation forces equals mass times acceleration, you also had that it was equal to mass times dv dt. And again, these were both only true for constant masses. But in fact, if you write it the way Newton did, then it's also dp over dt, where p is defined to be mass times velocity, at least until we get to relativity. Okay, so those are all options about how you could write Newton's second law. Well, it turns out you could also write Newton's second law for torque in a similar way. The summation of the torques is equal to I times alpha, where I put a vector there, again, reminding you it's a pseudo vector. It could also be I times d omega over dt, but it could also be dl over dt, where L equals your angular momentum which is given as a vector as L is equal to R cross P, which is normally R cross MV, right? Now, the magnitude of that is also just I omega. So that's another version we could use as well, okay? Now that we have all those out of the way and have introduced those equations, and in fact, you can derive them from Newton's laws. Your book does that. I just didn't take any time to do it. But now that you have that, let me show you a couple of tricks on calculating moment of inertia. So this is one of those things where you're actually doing calculus in a calculus-based physics class. So it's something you need to be able to do. What we're going to do is I'm going to draw a vertical axis and a horizontal axis. And that's going to be my x-axis. That's going to be my y-axis. And now I'm going to imagine a rod whose diameter is way smaller than its length. So this would be length L over 2. This would be length L over 2. And let's assume it has a mass M. So what I'm telling you is we know M and L. But what is I? Okay, so that's what we're going to calculate. Now, what I'm going to do is I'll write the integral I of, well, I should say the moment of inertia equals the integral of R squared dm. Okay, now the trick is when you go to do calculus with integrals and stuff like that, when you're doing actual physical objects, there's a danger that you might make the physical object into a small part that you're going to integrate, but you can make it in such a way that you're going to have to cause yourself a lot more work. So if you look at this, what you have to do is imagine some differential mass element, the dm that I'm talking about. And what you want is that dm to not change significantly in the variable r from one part to another. And you don't want the r to change from one part to another very much. So what you ideally do is try to find something that is oriented perpendicular, say, to an r vector. That means a vector that points out from the origin or from the rotational axis, and then it's only infinitesimally thick from there on out. So what I'm going to do is I'm going to say, okay, let's imagine this. Let's imagine this little slice right here is dm. Now I'm going to imagine that little slice is a distance x away, and the thickness of that little slice is dx. Okay, and I'm saying that L is much greater than R, where R would be the radius of this little rod. Okay. The reason why I say that is because if the R is really big, then the distance, say, from this point on the axis to this point is quite a bit longer than it is to this point from the axis, or to this point from the axis. So each of those things would have to be dealt with. But if it's really thin compared to the length, then there's not an appreciable difference between the top edge and the bottom edge and the middle edge of that differential mass element. So I'm going to say dm, this thing seems to have linear properties, right? It looks like it's a thin rod, so it's really sort of like a one-dimensional thing. And that should lead you to realize that you're going to use dm equals lambda DL because it's linear. You know, it's very thin, linear, almost one-dimensional. But what we see is for DL, we're going to use DX. So in fact, in our case, DM is going to be equal to lambda DX. And we can already figure out what lambda is. Lambda, which if you saw from what I wrote earlier, DM is equal to lambda DL, then that tells you lambda is DM over DL. But if it's homogeneous, then it's a constant. Okay. So like I said, any cubic centimeter I cut out of that rod and weigh is going to weigh exactly the same as any other cubic centimeter I pull out. Since that's a constant, then I can just take the lambda and define it to be the total mass M divided by the total length L. That's it. So not only am I putting it in terms of lambda, I already know lambda, so it's no big deal. So let's go about working our problem. So I got now I is equal to the integral of R, which you can see R is supposed to be the physical distance from it nearest point basically on the rotation axis to the actual mass element. And that distance is clearly X from the diagram. So we're going to say X squared, and then that's going to be times lambda dx. And obviously we can pull the lambda out in front, and I'm going to get lambda times the integral of X squared dx from X equals negative L over 2 to X equals L over 2. So I can now say I'm going to go ahead and substitute that lambda. I'm going to say that lambda is M over L. And anybody want to tell me what the integral of X squared is?
X cubed over 3.
Yes. So you're going to write X cubed over 3, and we're going to evaluate that at negative L over 2 and positive L over 2. So this is going to give us M over 3L times when I cube L over 2, I get L cubed over 8, and then I got to subtract from it L cubed over 8, but negative. Of course, when you cube a negative, it comes out negative again. So I'm going to go ahead and not write what I just wrote. I'm going to write it like this. I'm going to say it's negative L cubed over 8 again. So you see the minus and minus makes a positive. So minus minus becomes plus positive. So from that, you can see that L cubed over 8 plus L cubed over 8 would be 2L cubed over 8. 2 over 8 is, of course, 1/4. And I already had a 3 in the denominator. So now I've got I is equal to M L cubed over L times 3 times 4, that's 12. Notice this L cancels out with one of those L's, leaving a 2. So I get, in fact, the answer is 1/12 ML squared. And if you look, there's a table in your book, in the online book, that is, and they actually give you the actual table of indices, or excuse me, of moments of inertia. And I was thinking it was in section 10.9.1. Maybe it's not. Maybe it's in. Nope. Maybe it's 10.9. Nope. Maybe it's. Let's try this one. Okay, still looking for it. One more time. So I'm looking at section 10.6 now, see if it's there, but I saw it. No, it's not there. So how about 10.5? Yes. at 10 in section 10.5, there's a table called figure 1021. There's a table of I's for various values, and looking at a rod rotated about the center, you get 1/12 ml squared. So that's exactly what we got. So I'll say this is rod about the center. Well, what about that? What happens if I don't rotate it about the center? Well, I can draw a new coordinate system again. Let's do that. I'm going to draw a new coordinate system. There's my new coordinate system. This is my y-axis. This is my x-axis. Again, we're going to assume the radius or diameter is way smaller than the length, and our object is going to look like this. Okay, and this length right here is L, and again, its mass is M. Again, I'm going to choose a differential mass element, dm, which equals lambda dx, because this distance from here to here is dx, and this distance from here to here I hate when it does that. Just thinks that it knows what I want and it don't. Yeah, that didn't go out very well. I'm really obsessing about this. I'm sorry. I shouldn't be. Aggravating. Okay, what I'm going to do is say this distance right here is x, and it goes out to right here. Okay, so that is in fact the distance from the rotation axis. That's what I'm trying to show here, just like that was what I was trying to show up there. So that is the r squared in the formula. So now I can write I equals the integral of r squared dm, which equals the integral from x equals 0 to L of x squared times lambda dx. Again, we know that lambda is m over L, so I'll put the m over L out front, and I get the integral of x squared is 1/3 x cubed. So I'm going to say this is 1/3. And then I'm going to say x cubed, but I'm evaluating that at 0 and L. The 0 is going to obviously give me nothing, but I will get m over 3L times L cubed, like that. Obviously, this L cancels out with that 3, leaving a 2. So ultimately, my I about the end is equal to 1/3 ml squared. And that happens to be one of the formulas on that table as well. Okay. It turns out there's another way you could have done it. It's called the parallel axis theorem. There's a parallel axis theorem that says I about any particular position is equal to I about the center of mass plus m times h squared, where h is the distance from rotation axis to the center of mass. So we know, for instance, the center of mass for this guy is at x equals L over 2. So in rotating that about the end instead of about the center, I don't like this one. I'm going to go ahead and erase it somewhere else. The center of mass is at x equals L over 2, and that implies h is equal to L over 2. So if I do this calculation, I've already did it about the center of mass. That was the first one we did. So I is going to equal 1/3, or excuse me, 1/12 ml squared plus, now I just write m, and the distance between the center of mass and the end is L over 2. So I'm going to write L over 2 squared. That's going to give me a common ml squared that I'll pull out in front, and that'll be 1/12 plus L squared would be L to the 2 power would be L squared, which I got, but 2 to the, or 1/2 to the 2 power would be 1/4. So that's 1/4. But to get a common denominator, we know that I have to multiply the bottom by 3. And if I multiply the bottom by 3, I got to multiply the top by 3. So I get 3/12 plus 1/12 is equal to 4/12. So inside of here is 4/12, which reduces to 1/3. So we get 1/3 ml squared is I about the end, which is exactly what we got the other way. That cool? Any questions on that? Let's go ahead and do a little bit more tough one, and that'll be the last moment of inertia I calculate for you. Sphere's kind of hard, so unless if you know how to do multiple integrals, the sphere could be nice then. If you don't know how to do double and triple integrals, the sphere is kind of a mess. So unless you've done Calc 2 at least with double and triple integrals, which often I don't think it's even covered until Calc 3, then you could try to do the sphere, but this is a good enough exercise, period. So what I'm going to do now is I'm going to draw another coordinate system. And that coordinate system is going to look like this. Let's see if I can draw it pretty well. I could, but I didn't want to. Okay, that's pretty good there. And let's see. So this is going to be my x-axis. This is going to be my y-axis, say. And then my z-axis comes out of the board. Okay, now what I'm going to draw is a cylinder. Okay, now let this come down here. There's your cylinder roughly. Whoa, Nelly. Okay, I'm not happy with this being tilted down like this either. Oh, let's delete that thing. Oh, I forgot how to delete. Oh well, we'll leave it be. That's supposed to be a perfect cylinder. Okay, I'm going to say we know these quantities as well. The quantities that I'm saying we know is we know this height h, and we know the radius big R, and we know the mass m. Okay, this is one where you're going to use an actual volume as opposed to an area or a length. So what I'm going to do is I'm going to calculate what that is. So I'm going to imagine a spherical, or excuse me, a cylindrical shell. I don't like that shell. I don't like that show either. Okay. And now just outside of that is the outer edge, dang it. Of the shell. And this shell is going to go all the way down to the bottom. This part's going to go to that part. That just turned out bad. Anyways, I think y'all can see what I'm trying to do. This distance right here to the inside edge is R, but this thickness right here is dr. Now, technically speaking, if I cut this and laid it out flat, then it would look like this. Where this length from here to here is 2 pi big R. And this length from here to here is H. And in fact, when I cut it, that inner side is actually a little shorter than the outer side. But if you were able to ignore that little triangular prism there on each end, then we could say dm is going to be equal to rho dv, which is rho times 2 pi r dr times h. Okay. Now you can see I'm making an approximation there because it's only if those little triangular prisms at the end are negligible that I can actually do this. Otherwise, I've got a wrong figure. Well, what this shape really is, the red cylindrical shell that I put in there, is a cylinder of radius r plus dr, having cut out of it a cylinder of radius r. So the actual volume technically is dV equals pi. It's pi r squared. H is a general formula for a cylinder. So I'm going to factor out the pi and the H right here. But what I have left is the r squared basically for each case. So the outer radius is r plus dr. And that'll be squared, and the inner radius is just r, so that'll be squared. So the formula is actually going to be pi times h times, now I get r squared plus 2r dr plus dr squared minus r squared. Everybody see the math I did there? Everybody understand how I did that? So if dr equals 0.0001, then dr squared equals, this is tenths, hundred thousandths, 10,000. So this would be 1 over 10,000 squared. And that is in fact going to be 0.0000000. I think that's right. So it'd be 10 to the 8, 10 to the negative 8. Yeah, 7, and then 1. So I think that shows you that in fact dr is quite negligible compared, or excuse me, dr squared is quite negligible when compared to dr. These r squareds cancel out. This dr squared is very much approximately 0. Okay. So that's why we're okay with using that differential volume element that I drew up top, where I just imagined it was basically something that had a length of 2 pi r, a thickness of dr, and a height of h. So I got 2 pi r dr. And notice what's left is pi times h times 2 r dr. So we're actually done with that. So now let's work on the moment of inertia. So I is equal to the integral of r squared dm. I know I'm going to integrate from x equals 0 to x equals big R. And I could use R here, but I'm just going to picture it in the X direction. Actually, no, I won't. I'll use the little R. Let's do this. Because that R is that shape right there. So I'm going to call this R squared times 2 pi h times r dr. I just put them in a better order, right? So that's all that happened there. Now I'm going to take and pull those things out. Oh, I left off the row too. So let me put the row in there. So I'm going to pull those things out and I want to say 2 pi rho h is all outside. Then I get the integral of r cubed dr, and that's going to be from 0 to big R. Now notice rho has to be equal to m over pi r squared h. Everybody agree with that? Rho equals m over pi r squared h. Because we're assuming it's a uniform object, so the average density is really the density, and the average density be m divided by v. The volume of the actual blue sphere or blue cylinder is pi r squared h. So that's why I got that. So now I can go ahead and substitute that in for my rho. I'm going to say this is 2 times pi times h. Now I'm going to put an m up top and I'm going to put a pi r squared h on the bottom. And you can see that the h's will cancel out, that the 2 will cancel out. And that's basically it. Now the integral of r cubed is going to be 1/4 r to the 4th. And when I evaluate that at r equals 0, I get 0. When I evaluate it at big R, I just get 1. I get, well, let's say it this way. Let's say it's r to the 4th over 4. Now you can see that r squared is going to cancel out with 2 of these and leave a 2 there. And 2 divided by 4 is going to give me 1/2 mr squared. So the moment of inertia I for a cylinder is equal to 1/2 mr squared. That's how you do that. Anybody have any questions? No questions on that? All right. So that's the kind of thing you should be able to do. Obviously, those rods would be a good example. I could make one that's more complicated to test you on. Like, for instance, what if in the case of the rod, what if lambda was proportional to r squared, meaning the density got larger and larger and larger the farther you got from the end. So maybe the center is made out of balsa wood, and after a centimeter or so, it turns into a heavier wood, and into a heavier wood, and into a heavier wood, and into aluminum, and then it turns from aluminum into steel, and then from steel into titanium. Well, not titanium, let's say plutonium or uranium or something like that. Then that could actually model an object that has much more mass per unit length as you get further from the edge. The only difference would be now you're going to say I is equal to the integral of r squared dm, but dm is going to be lambda as a function of r times dl. So you might say lambda is equal to some constant k times r squared. If I gave you the total mass, or I said the total mass was m, for instance, and I gave you the total radius, which I said was r, okay, then you could integrate this, find out what that is, and determine what k is. So that's a very typical problem for me to ask my students is, okay, assume lambda is k times r squared, and calculate the moment of inertia for a rod with that density rotated about its center. So you'd end up writing I is equal to the integral of r squared k times r squared for the lambda times, now we're going to use our volume. It's going to be just that was the lambda just times dx. And we're going to integrate that from negative L over 2 to L over 2. So now it's just a little more complicated, and that's the whole point, is I want you to be able to do these problems and set them up. Now I've set one up for you whose linear density is proportional to r squared, and I could ask questions like, assuming m is just big M, and you might even say that's 10 kilograms. For instance, I could give you a number if I want. I usually wouldn't give you a number. And the total radius is big R, which I could say is maybe 70 centimeters or something like that. You could actually integrate that and say, what will K be? What are its units? Okay, so that's another question. And then I equals question mark. So that's the type of problems we could ask you with that. Anybody have any questions on that? Okay. So let's try another. This time we're going to actually use the torque equation. Okay. So the summation torques is equal to I times alpha is what we're going to be using. What I'm going to imagine is, in fact, an inclined plane that makes an angle theta and has a sphere rolling on it. Now let's say a cylinder. I like a cylinder better. Let's say this is that has a mass m and a radius r. Okay. So that implies I is just equal to 1/2 mr squared. So we know the I already. That's a good thing. Now I'm going to draw a coordinate system, and so we can make our well, I want to make a free body diagram basically, but now there's 3 different free body diagrams, or 3 things that you get from a free body diagram. So what I'm going to do is I'm going to draw an axis again. And the x-axis I'm going to try to make parallel to that, and then the y-axis I'm going to make perpendicular to that, like so. And now I can't pretend like the ball is actually a sphere anymore. I mean, it's actually a point particle anymore. I actually have to assume it's got sides to it, because what's going on here is we have a weight acting on it. That's equal to big M times G. Now that breaks up into, since I drew this as the X component, or as the X axis, and this is the Y axis, I can break this up into components. The negative component along the Y axis is this, and then the positive component is along the X axis is that. And since this angle is theta, then so is this angle. So this is mg cosine theta, and this one over here is mg sine theta. We also have acting on it, however, a normal force, Fn. And in fact, I'm going to assume rolling without slipping. Now, what does that mean? Hopefully I'll have some understanding just from hearing the words, and that would be an ideal scenario. But if not, it's understandable. You maybe haven't thought about such things before. So rolling without slipping means basically if the block, the cylinder rotates by theta equals 0 to theta final equals 2 pi, then the distance traveled will be, anybody want to take a guess of what that will be? Where'd my chat go? There it is. Yeah, thank you, Adrian. That's just all your. So nobody answered. So what I'm going to tell you is that the distance traveled, let's call it X, is actually equal to R times 2 pi, which equals 2 pi R. So in other words, the bottom of the cylinder is moving at exactly the same negative rate as the center of mass is moving down the cylinder, so that it's actually always in contact. The very bottom's always in contact and in a static friction situation. And that's forcing the object to roll over, where if it covers 3 inches of circumference, then it's going to have moved 3 inches down the plane. Okay. That tells us that 1 S or X is equal to R times theta. That also tells us, if we take the derivative, that V is equal to R times omega. And then also says that if we take the derivative of that, A is equal to R times alpha. So I've got those forces drawn, and I have another force as well acting in the negative X direction. And that's going to be my friction force, which I'll write as just a fancy F, a curly QF, if you will. That's the worst F I've ever seen in my life. I hate it. Okay, so there's the F. So let's do our free body diagram, or let's take this free body diagram and write out the summation of the forces in the Y direction equals mass times acceleration in the Y direction. Are we, given the situation we're in, are we going to have any acceleration in the Y direction? We shouldn't, should we? So this acceleration is going to be 0. If we had acceleration, it'd be like bouncing up and down or something, or it just take off from the surface and start flying upwards and speeding up or slowing down, or it would dig into the surface or something like that. We clearly don't have any of that going on. So what we're left with is Fn, which is in the positive direction, minus m, oops, wrong m, minus m g cosine theta is equal to 0. So equation 1 tells us that the normal force is equal to mg cosine theta. Well, that's good because our friction formula is normally a mu static times the normal force. That helps, right? Now we're going to do the summation forces in the x direction equals mass times acceleration in the x direction. Only this time we expect it's going to accelerate because the friction should be sufficient to cause it to rotate. Now I can handle all these sign things I was telling you earlier. Let me go ahead and do that right now, just to keep me from forgetting. If this is x and this is y, what you can do is do this sort of thing. And that tells everybody, hey, positive is to the right, positive is up, and positive is counterclockwise rotation. In this class, it would be, or this particular problem, it'd be better to tilt that x-axis parallel to the other one. And of course, I would do that, but I just want to let you know that's the way you can do it. So now that we have the summation of forces in the x direction equals mass times acceleration in the x direction, we just have to add up the forces. And the positive force we have is the mg sine theta. Darn, that was a scary sound I just heard. So I say mg sine theta minus the friction force is actually equal to the mass times the acceleration. Does that make sense? Now that acceleration is technically the acceleration of the center of mass. The center of mass of the cylinder. Okay, so this will be equation 2. Now I've got the summation of the torques, which I'll write in red again. The summation of the torques is equal to I times alpha, is what I'm doing now. Now, in this case, what I see causing a counterclockwise rotation is nothing. And what I'm going to do is I'm going to use my pivot point to be the center of mass. So let's say right here is the center of mass and the pivot point. So in other words, that's the center of rotation. I can actually use that point, or I could use this point down here if I wanted to. It doesn't really matter. Normally you choose one such that it can take a force that you don't know and make it disappear. Because on the torque equation, any vector that points toward or away from the pivot point, or anyone that's actually acting on the pivot point, has no lever arm and therefore will give you 0 torque. So in this case, I've got exactly 1 torque and it's negative because the normal force acts on the center of mass, points radially outward. The gravitational force, mg, points down from the center of mass. So we don't need to take that into account. But what we do have is negative friction force times, notice it's already automatically perpendicular to the radius. So I'm going to say F times R is the actual torque. That's equal to 1/2 m R squared. That's the I times alpha. So this is equation 3, but we have unknowns. R, we don't know A, we don't know alpha, and we didn't know Fn, but we do now. We've worked that part out. And we didn't know we didn't know the friction force or the mu, whichever one you want to use. Okay, So that means we need 1, 2, 3, 4, 5 equations, or excuse me, 1, 2, 3, 4 equations. We've only got 3 so far. Well, luckily we know, as I said up here, as a result of rolling without slipping, we could use one of these. And in fact, what I'm going to use is A is equal to, let's not do that in black, let's do it in red. A is equal to R times alpha, and that's equation 4. Any questions on that? Now we might be off by a little bit of a negative here, because notice here, if alpha rotates in a clockwise direction, that's consistent with the A going down the incline, which we call the positive direction. So I might have to deal with that. But in general, we got something we can work with now. I can take equation 3. So solve equation 3 for F and put it in equation 2. So when I do that, I get basically F is equal to negative, notice one of these R's can cancel out here, negative MR alpha. Oh, that's it. Oh, over 2. Okay. So that means I'm going to put that in equation 2. That means I've got mg sine theta minus, and here's the negative thing that we got to pay attention to, because I'm not sure it's going to work out this way. I'd normally like to make all the coordinates positive if one of them's positive. So and by me choosing downwards acceleration to be a positive A direction, I would have normally chosen to make clockwise torque positive. So this might bite me in the rear. We'll see in a second. So there's the mg. And now what I'm saying is I'm replacing that friction force with it. So that's negative mr alpha over 2. And that's all equal to m times A. Well, now I can apply 4 because alpha is actually equal to A over R. So now I've got mg sine theta. Again, I'll put a question mark over that. That's going to be m, or 1/2 m R times alpha, which is A over R, and that's equal to MA. Now you can see the 2 R's cancel out. And in fact, everything's got an M in it, so I can divide through and get rid of M. And I'm ultimately going to find out that A is just equal to G sine theta. And again, I'm going to put a question mark over this. 1/2 A. So I pull that to the other side. That becomes either 1/2 or 3/2, depending on what that sign is. So I'm going to say, if I pull this over here, it'll be 1 minus 1/2. So it'd be 1/2 A is equal to, that's again, it could be that, or it could be 3/2 A. But that's going to be equal to G sine theta. Or you could say A is going to either be equal to 2G sine theta, or it's going to be equal to 2/3 G sine theta. Now, do you think this thing can fall faster than something sliding? I would say no. That's just and you can see an example where your book explained why that wouldn't happen. So in fact, we've got to conclude that the 1/2, the equaling 1/2, which would be sort of equivalent to that being a plus symbol. So I was right. I really needed to change that symbol to a plus because it's inconsistent with the A. So in fact, our answer should be 2/3 G sine theta for A. So the big thing to learn here is what I screwed up with was choosing my coordinate directions as arbitrarily positive in the X direction, which is down, positive in the Y direction, which is up, and positive is counterclockwise. I didn't have any freedom to do that because I actually need to write. If I did that, I would have had to make equation 4 be A is equal to negative RA. That would have worked as well. So this all worked. Now that I have A, I can go back and, for instance, plug that into equation 3, and that would actually give me, well, I could first use equation alpha equals A over R to figure out what alpha was. Then I could put alpha in equation 3, and that would let me figure out what friction is, and so on and so forth. Okay. So that's kind of neat. Now we have an actual way to figure out what friction is necessary to let the thing roll without slipping. And we found a way to allow something to accelerate. I did not finish all of it, but your time's up anyways. So I'm glad I at least got you to be able to see the integrals for the moment of inertia. And oh yeah, I did say theta final earlier just because I was wanting you to realize that I'm starting at theta equals 0, and then theta final after it spun 1 turn. I was trying to show everybody what that meant in terms of rolling without slipping. So that's why I wrote that. You stole my gig, Miana. All right. If you guys want to, y'all can work that out. You can go back and change my sign convention to make it counterclockwise as negative and solve it again. I'll give you extra credit for that if you'd like. But this is actually correct. The only thing is I had to work through whether it's positive or negative is going to be right, just because I chose arbitrarily what direction it was. So the equation alpha equals R times, or A equals R times alpha, is not right. I had to put a negative in there if I was going to do what I did. And if I'd done that, then it would have gave me that 2/3 G sine theta. All right, you folks are free to go. I'll wait for the last person to leave, and then I will stop shop. And I will see you next week. I probably will send you a message when I put the practice test up, but you're free to go.
I have a question.
Uh-huh.
I was wondering, is it okay if we take old practice tests?
Absolutely. Oh, well,
Okay.
wait a second. No, I can't. Yeah, I can't do that, but I would have to make all new ones just because I don't want to give anybody credit for taking practice tests that they took after the test was over. That's why.
Okay.
What I'm going to do is maybe I'll make I might just make one. I don't want to get the problems, the practice final so big that people don't take it. What I was thinking about doing is putting all the banks in and just, allowing you to take it, one question at a time. But it covered 1 through 6, so you'd have to do 6 questions to get one of each chapter every time. I could do that, but 6 might be a little onerous for a practice problem. But I think that's what I'm going to do. I probably will. I'll make up a final, and it'll literally have 1 question per chapter instead of what I had before was most of the stuff came from the last chapters.
Thank you.
No problem.
Professor, I have a question.
Go for it, Jamie.
So in the grades section for those primers that we did at the beginning of the semester that were duplicated,
Right.
one of them, the fake physics primer, it's dropping the grade for the one that I actually did, and it's including the 0 for the one that I didn't do.
I'm glad you checked that mathematically, because that's always the big question if I did it right. Let's see. And you're saying is it the faux introduction that you did well? Or the faux primer?
Well, on mine it says that it says actually that the introduction to mastering physics and the physics primer are both being dropped, and the faux introduction and the faux physics primer are being kept. But for some reason, I do have a grade for the faux physics mastering physics, but not for the physics primer.
Okay, so I see you've got physics primer good, and it's giving you a score that's quite good. And I see that you got a intro to mastering score that's pretty good. Let me see what the faux intro to mastering. It's got the same as your faux intro to mastering. Let's see what your faux primer is. Oh, okay. I see. Yeah, your faux primer is 0. If it's counting that one, that's a problem. Look in the grade section real quick and fix that.
All right.
You can wait while I do it. Anybody have any questions while we're waiting on that? While you're waiting on me doing that, I should say.
You have a good night. All right.
You too. Thanks, sir. Appreciate everybody coming. Appreciate your patience, everyone.
Oh, I have a question.
Go for it.
Did you receive my scratch work from the exam?
Yes. Yeah, I think I got
mine was over Zoom. I don't think it went through.
Oh, what's your last name?
Novoa, N-O-V-O-A. I don't think
I'll check. I didn't need the scratch work anyways, but I saw I got someone's in an email. That's why I thought it was you.
You didn't need it? Okay.
Yeah, I didn't need it either way. So yeah, what I show counting right now, Jamie, is introduction to mastering. That counts as a homework, and physics primer good counts as a homework. Let's see if anything else untoward. Yeah, the faux ones are listed as faux introduction to mastering physics. That's 0% total. So in other words, it has 0 weight, and the faux primer is under the 0 weight category as well. So but I am showing exactly one dropped grade in the grade book. So you might have maybe thought something else was dropped. I'm not sure, but yeah, it seems to be counting yours correctly.
Okay, well, I mean, it's just that like right next to the ones with the grades, it says that like this assignment is dropped, and it doesn't say that next to the other ones, but if it's not affecting my grade.
Yeah, it shouldn't be affecting your grade. And I do a calculation myself at the end of the semester. I download all these grades and build my own spreadsheet and throw it in to make sure it's right. And normally it always is right, but just to make sure, I always do that. So it would catch it at that point.
Okay, that's good to know.
Okay. All right. Anybody else have any questions?
Yeah, I do. For the imported assignments, are those all counted towards the grade?
No, none of them are supposed to be counted at all. There's a column in your grade book, or it might be a row in your grade book, that says imported grades, and you'll see the weight of that is 0.
Because in the row that shows a percentage, it doesn't show 0 on mine.
Okay, I'm looking at the setup right now. I've got, as far as the grades set up, it shows, I'm trying to look at just, oh crap, it did something I didn't mean to do. Crap, move, crap. Just erase it. That's just pain in the butt. I hit 2 fingers on my mouse pad instead of 1, so it just shifted the whole screen out of whack, which made it really nice. Okay, I'm flipping through. I don't see anything there. What's your last name?
Mackenzie.
Mackenzie. Gotcha. Just checking to see if anything pops out.
Gotcha.
Okay, that looks good. So yeah, it shows 10% for the online test. It shows 20% for the homework. It shows 5% for conceptual, 20% for lab grade. Practice test is 0. You know how that's supposed to count. That just means it's extra credit at the end of the semester. Lab reports is 0. Lab attendance is 0.
You're talking about the weighted part on the top.
Yeah.
Oh, gotcha. I was on the bottom.
Gotcha. Yeah. So I'm looking at that part. That's where it tells me what the weights are, and anything that's 0 shouldn't be counting towards your grade at all.
Gotcha. Okay.
Okay,
All right, thank you.
no problem. Anyone else? All right, well, I guess I'm gonna say, yeah, go ahead, Jamie.
Oh, yeah, I was gonna say, there was a problem from one of the practice questions from the textbook, from chapter 9
Right.
that I've been having trouble with, and I want to know if it's something that I should continue working on because it is something that we might be tested about,
Okay.
or if it's something that I can just throw in the towel and give up.
Let me let you share screen so I can see what one you're talking about. I've now clicked it to allow you to, so if you want to share your screen, you can.
This one. And technically 35 too, but if I get this one, I might get that.
Okay. So determine the fraction of kinetic energy lost by a neutron when it collides head-on elastically with a target particle at rest.
Yeah, no matter what I do, I always get something like I get like V1 equals 0 or V1 equals V1. And
so if this is the question, notice it says something key here. It says determine the fraction of kinetic energy lost by a neutron when it collides head-on and elastically with a target particle at rest. Elastic means kinetic energy is conserved, so it should lose none.
So the answer for the first one is like 1 point. It's not like kinetic energy lost like total. I think it means the amount transferred from the neutron to the other
okay,
particle.
yes, yeah, I got you. So you're just trying to say how much just the neutron. So yeah, I got you. Sorry about that.
Yeah, and I've been having trouble figuring that out because I'm like, okay, so obviously I have to use the two formulas and I have to solve one for the other.
Yeah, you're using, since it was sitting still, you can use the formula that we derived, which is what those parts are in problem 34. You just have to use the mass being for the elastically with a target particle at rest, which is, so in the first, you did the first one, you got that right, or you get that part wrong too?
So I haven't been able to get any of them right. The closest I got was for the first one. I think I solved that. I made several attempts. So I think for that one at some point I got like V1 equals V2 or something. And I was like, so is this the one where their velocities switch?
Gotcha.
And so I keep getting different answers.
This is definitely a fair question. I'm not sure I would put it on a test, but it's definitely the level and the type of problem I wouldn't mind putting on a test. And really what we need to do that is, or to solve that would be use the equation that we employed in chapter 10, I think it was. So let me do that real quick. I'm going to pull up the chapter 10. Actually, it wasn't chapter 10, it was chapter 9, sorry. So collisions in one dimension with elastic collisions, that was section 9.5, if I remember correctly.
Yeah.
So when we work this out, what I ended up getting is, yeah, the exchanging of the velocities when they're in elastic collision. And they gave us an actual formula. So basically what we have is, after the collision, the first particle that was moving, which is the neutron, should actually have a velocity given by VA prime equals MA minus MB over MA plus MB times VA. So that's the expressions we're using. VA prime, which is for the neutron. I'm going to share this in a second. Hold on. Which is equal to MA minus MB over MA plus MB times VA. And then VB prime, that's supposed to be the 2MA one, if I remember correctly.
Yeah.
Yep. Yeah, the 2MA over MA plus MB VA. Okay, so I've gotten all that written down. Let me record the masses from that. You said the neutron, did they give you the mass of the neutron?
Yeah, the neutron is 1.01.
Okay.
And the first mass is also 1.01,
Okay.
which is why I kept ending up with, for this part at least, I kept ending up with the velocity equals 0.
Mhm. Well, the neutron and proton, well, if they're both equal in weight, which the neutron and proton shouldn't be, there is a slight difference in them, but they might not be doing it as well as what you're thinking. But in other words, they might not care about the number of sig figs you're going to. They might only do not enough sig figs to see the difference. What does it say the mass of the proton is? You said that's 1.01 as well?
Yeah, they're both for A, they're both 1.01.
Okay. So VA prime is really the velocity we're looking for. And that is supposed to be 1.01 minus 1.01 over 1.01 plus 1.01. But obviously that's going to give you just 0. So the entire kinetic energy is what it lost. How much speed did it say it was had initially, or did it not say?
I didn't give the initial velocity.
It didn't give it?
No. That's why I was confused, because I was like, so I'm solving for 3 variables with 2 equations?
Right. You I'm trying to look it up right now. That was problem 33, right?
Yes.
I forgot I had the book open right here. Okay, determine the fraction of kinetic energy lost by, okay. So in the first case, the fraction of the kinetic energy loss should be 100%. Is that what you what you got and it said was wrong?
Well, no, the back of the book just says 1.0, so I'm assuming that that's supposed to mean all.
Exactly. So that's right. That's exactly what we found by using those formulas. So part A was right. Part B, they said we're going to run into a heavy hydrogen, which is 2H2, or excuse me, 2H1. So in this case, we're going to have VA prime is going to be equal to MA minus MB. MA is 1.01 U, and MB is 2.01 U over 1.01 plus 2.01 U in that case as well, times VA, which should be basically just -1 over 3.02 times VA. So the fraction of the kinetic energy loss would be 1/2 MA. Oops, I ain't sharing this with you. Let me share it with you. So the initial kinetic energy is 1/2 MVA squared. The final kinetic energy is, whoa, what just happened? I think I just touched the stupid button again. Nope, that's not it either. There it is. Okay, the final kinetic energy is equal to 1/2 MVA prime squared. So the fractional loss in kinetic energy should be KE final minus KE initial over KE initial. That's what they're asking for. So this is going to be 1/2 MV M neutron VA squared. Actually, that's supposed to be the other way around. Sorry about that. So 1/2 MA VA prime squared minus 1/2 MA VA squared over 1/2 MA VA squared. So I think you can see that there's a lot of cancellations go through here. Like those 1/2s all cancel out, those MAs all cancel out, and you're left with basically VA prime squared minus VA squared over VA squared, which you could simplify as VA prime squared over VA minus 1. Oh, nope, that's, yeah, that is squared down there, sorry. So this should be squared too. So if we do the second part, then what we're gonna have is VA prime should be equal to -1 over 3.02 VA. So this becomes fractional kinetic energy lost becomes -1.1 over 3.02 VA over VA, and that should be squared actually. So when I do that math, when you check to see if it works out, you do 1 divided by 3.02, and I'm going to square that if I could write it correctly. I'm going to square that is equal to 0.1096 minus 1. So it says the fractional loss is about 89%.
Yes.
And it took that, or that's supposed to be the right answer?
Yes, I mean, that is what they said the right answer was.
Okay. Do you see the difference there? I worked it out, manipulated it, in symbolic form, which is ideal if you can do it. And this problem almost is impossible to do it without it. But what you can do is you can just, if you, I know you don't like working symbolically like that. If you wanted to, you could just plug any velocity in there and just say it's 10 or something, and then consistently work it out and then do that same fraction. But by reducing it down to VA prime squared over VA squared and then -1, just remember they're asking for what the loss is, and this formula is automatically going to give you negative. So
Okay.
you just drop the negative and do it.
All right, so that makes much more sense.
Good. Glad to hear it.
All right. Do you mind if I ask one more question, or has it been long enough?
Now go for it.
Okay, so I also had trouble with 35, and I don't know if it's like the same thing, but it's 2 objects, one initially at rest, undergo a 1D elastic collision, one-dimensional. If 1/4 of the initial kinetic energy is transferred to the target, what is the ratio of their masses?
Okay.
Is that one like we don't have to worry, it's not going to appear on a test?
That's pretty tight. I don't think I'd ask that on a test, but it's definitely not unreasonable to have on a test. But the good news is you can still use the same thing that we use to find the change in our lost in kinetic energy. That formula that I just found, VA prime over VA quantity squared -1. So what you're going to do is you say if 1/4 of the initial kinetic energy is transferred, what that's meaning is you're saying the answer is going to be -0.25. So you have VA prime. Let me show you on this paper. I'm going to write in red since I don't want to move more space. I'm going to say delta K over K is VA prime over VA squared -1. What you're saying for number 35 is this should be -0.2. 25. 0.25. Okay. So if you set that equal to 0.25, you can solve for VA in terms of VA prime in terms of VA. So if 1/4 initial is transferred, what is the ratio of their masses? Okay, and you can then, once you have VA and VA prime, you can figure out how to set that up in the VA prime equation right here.
Okay.
So you could, like I said, solve for VA prime over VA, but do it with do it for VA prime in terms of VA. That'll give you like some percent with some ones on it or something like that. And you can just stick it over here in this part. And when you stick it in that part, that'll allow you to solve for the masses. But yeah, I would not be putting that on test. That's a little complicated. It's a fun problem to work, but it's more of one that I'd be tending to give that to a student in a homework setting.
Okay.
Yeah.
All right.
I like that you're doing homework out of the book. Is you? I assume you're doing that like after you've done the school, the assigned homework, or are you doing it to help you get to the?
I'm doing it to help me get to the homework. I'm doing the homework in the textbook as I finish the sections associated with them to see whether or not I understood.
Well, yeah, that's an excellent thing to do that will help you immensely.
Yeah, I just have to hurry up and finish 9. It's only 3 days late.
Yeah, that don't bother you too bad. Don't worry too much about that.
I'm not, because I only have one stomach, and if I give myself an ulcer, it's going to be a little bit troubling. So.
Exactly.
All right. Well, thank you for your help.
You're welcome. Have a good one, Jamie.
You too.
Bye-bye.
Bye.